Excellent. All right. Good morning, everyone. Thank you for being here. This is the first talk of Work in Progress series, and we invited Dr. Umair Mohammad to give us this talk. So let me do a brief introduction. So Dr. Umair is a postdoc fellow in Saeed Lab at School of Computing at FIU. He earned his PhD in electrical engineering from University of Idaho in 2020. And broadly, his research interest includes machine learning, neuroscience, and machine learning over wireless edge for biomedical applications. So welcome, Umair. You can please start.
So good afternoon, everyone. Dr. Saeed introduced me quite nicely and my work as well. So I will jump onto the formal introduction. So basically, I will, or the topics that I will cover. So I will briefly expand on my education and training a little bit more, talk about my research experience, and that will be the bulk of the presentation, and then the proposed research or proposed projects. This will be followed by a brief cover or brief discussion of my teaching experience and some of my proposed teaching. I will conclude by summarizing my work and acknowledging the people who have helped me in my journey. As Dr. Said explained, I'm a postdoctoral associate at KFSCIS at FIU. And broadly speaking, I work in biomedical event detection with advanced deep learning, though recent work focuses on seizure prediction, both model design and making it capable over the wireless edge. Prior to that, I had my PhD, where I also worked on machine learning over the wireless edge. I earned the PhD in electrical engineering from the University of Idaho. Before that, I have a master and bachelor, both from King Fahd University of Petroleum and Mineral in Saudi Arabia. So, like I said, there are two thrusts to my work. I will cover both today. The first one is machine learning model design for seizure prediction. That includes designing new, more robust data set, as well as new deep learning architectures. I also work on making these machine learning and deep learning models capable of being deployed over the edge, both for inference and for training. And I will give some examples of my work that I have done in this area in seizure prediction and propose new direction. I also have grant writing experience. I'm a senior personnel on 3 research grants that were funded for a total of $575,000 US. I also won the American Epilepsy Society Fellowship in 2024 for my work in seizure prediction research. And following that, I applied first time as a PI to a grant for their postdoctoral research fellowship. So it's a small 50,000 grant, but my first PI experience. I have over 20 peer-reviewed articles in top communication society venues, more than 350 citations. I have extensive mentorship and teaching experience, including both undergraduate and graduate students. The work has resulted in peer-reviewed articles. And I also have extensive technology translation experience, and I will try to incorporate that whenever applicable in my talk. But over the course of those experiences, I actually interviewed more than 130 domain experts and got feedback on my work and on future directions. So before I delve into the first thrust, which is the deep learning model design, I would like to give a brief background on epilepsy and seizures. So epilepsy is a neurological condition that causes repeat unprovoked seizures. It affects nearly or over 65 million people worldwide. And within the USA, up to 3.5 million are affected. NIH estimates that there are at least 1.5 million people with active seizures in the USA alone. The seizures are like a heightened activity of the brain or heightened electrical activity, and they can cause wide-ranging symptoms from the simple one like short-term memory loss or a brief absence to much serious ones that lead to convulsions, falling, and can lead to injuries such as fractures. Seizure freedom is something that is not possible for everybody, despite the advances in drugs and in implantable technologies. Some people may develop drug-resistant epilepsy. Implantable technologies are exclusive and either due to their cost or due to health reasons. So in general, one of the most common techniques to track and manage seizures clinically is electroencephalography, which measures the brain's electrical activity. And it is so there are some solutions that exist for seizure detection, and I will speak to that more. But in general, it is one of the most accurate techniques because it is close to the source. It measures the brain's activity, right? And the way it is measured is that there are a set of electrodes that are connected on the scalp. There is also intracranial, but we will limit our discussion to scalp. So that gives rise to multiple channels. Each channel is the voltage difference between two electrodes. So it represents the voltage difference between two regions of the brain. So, like I mentioned, seizure detection is something that exists. However, there are also challenges over there. But the trend in general in the research and the literature is to develop advanced deep learning and machine learning models to predict seizures ahead of time using this EEG data. The hope is that with the advent of a reliable wearable technology, we would be able to deploy these models on the wearable sensors so that people can use them in their real life, and we may make a significant difference to the life of people with epilepsy, where they can get a warning for a seizure ahead of time. So what is seizure prediction? So ideally speaking, the people who have epilepsy, their EEG would be divided into four distinct stages. So the pre-ictal stage, which is just before a seizure, an ictal stage, which covers the main symptoms of the seizure, followed by a post-ictal recovery period, and then an interictal phase, which is the period of normal function. So the detection task is quite simple. It is just discriminating the ictal parts from the non-ictal parts, and it is easy because there are specific signatures of the ictal part. Whereas the prediction requires discriminating between pre-ictal and interictal parts. This is quite difficult because the pre-ictal and interictal stages cannot be marked clinically. They are not. They cannot be annotated. So the first challenge is that there is not a lot of structural difference between the two phases, or there are too many similarities. That makes the task challenging. The other challenge is that lack of availability of large-scale data sets geared towards seizure prediction. So there are quite a few geared towards seizure detection, but not towards seizure prediction. So, and then the other challenge, of course, is how to get a high predictive performance such that it is useful either in the home care settings or in clinical settings. So my work addresses both. In the first part of this first thrust, I actually developed a new seizure prediction data set that is subject independent. If you read the recent literature, they use data from the CHB MIT data set, which has a maximum of 23 subjects and only up to 200 seizures. And most of the work focuses on subject-specific seizure prediction. That means that if a new seizure type or a new epilepsy profile were to be visible to the model, it won't be able to predict the seizures. So that is why I actually leverage a data set that has more than 675 patients and more than 4,000 seizures to generate new seizure prediction benchmarks such that they are subject independent, which means the models will be more generalizable. So how do we do that? The research practice is to define two variables called the seizure prediction horizon, the SPH, and the seizure occur period or the occurrence period, which is the SOP. So the SPH ideally would align with the pre-ictal phase, whereas the SOP is a small gap that we put between this assumed pre-ictal phase and the ictal phase so that we force the model to predict ahead of time. So usually the data preparation is done in 4 steps. So if you look at the figure at the bottom, in the first step, we have the ideal EEG, which does not really exist, right, with the 4 stages. And then in the second stage, what we do is we exclude the ictal and the post-ictal phases, because if you are predicting at the ictal phase, you are already too late, right? So that is why we exclude that part from our data set. And then because the pre-ictal and interictal phases are not clinically marked, in the third stage, we make an assumption regarding the SPH and the SOP. And based on that, we define our pre-ictal phase. And additionally, we also add a precautionary gap time, just to make sure that the model does not confuse between pre-ictal and interictal phases. Once all of this is done, in the last step, we have an EEG that is divided into clean interictal and pre-ictal phases. very easy process, but very challenging because not enough data is available, or if data is there for many subjects, like the data set I use, a lot of subjects had significant amounts of interictal time deleted because maybe the clinicians thought that this is not, they are more concerned with the ictal phase. But in the prediction part, like for prediction researchers, we need the whole EEG to be able to extract enough amount of data. So these are some of the results. So if you see, I actually used 4 possible combinations of SPH and SOP, and this would have clinical implications, right? So if there are patients who report that they have longer amount of preictal phases, or they know far further ahead of time they can sense some changes in the body, then these are subjects for which we need to use models that are trained on longer SPH. Some people may only require a short time of warning, so then the SOP of 1 minute would be enough. However, some parents of young children may require that we have SOP 5 minutes so that they know a longer period ahead of time that a seizure would happen. So if you look at the figure at the top, we were able to create 12 benchmarks based on the SPH and SOP combinations, right? And the significance is that the data set or my tool that I created, it generates data that has up to 700 seizures at maximum. And it contains data from 120 up to 120 subjects with equal gender distribution between male and female, whereas the other data sets that are used in literature, like I mentioned, only 24 subjects with gender imbalances and a maximum of 200 seizures. So this was a significant contribution that we did towards the data creation. Now I would like to switch pace to the model design. But before I do that, let me just give a quick overview of the deep learning architectures we use. So in my research, I have mostly used what we can call the layered architectures, or architectures that have an input stage, an output stage, and a number of hidden layers in the middle that carry out some mathematical operation. For these, so I will skip the mathematical details in this overview, but we can discuss those later. So let's say that you have a data point, x1, right, that is given to the model. So the architecture that we use, typically what they would do is a forward pass. So it would pass them through the first layer, calculate the output, pass that output through the second layer, and so on until the last layer, right? So the second last layer, and then the last layer. At the end, you have an output. So for my case, the seizure prediction task, luckily we can distill it down into a binary classification task where we are only classifying our EEG segments into two, either preictal or interictal phases, right? So the output will be binary. In general, the output, the way we do it is we output a probability and define a threshold that if the probability is greater than 0.5, then we are going to do the prediction. But that happens in the inference, and I will explain that. But during the training process, once we have an output, we define a loss function, right? And based on that loss function, we perform the backward pass. So the model is passed, or the output is passed in the reverse order, and we update at each stage, we update the parameters of these hidden layers until we reach the beginning. Once we have reached the start, now we have done one data point. We can do other data points until we covered the whole data set, and that is known as one epoch. Multiple such epochs until we reach a desired performance level, such as accuracy, is going to complete the training process. At the end of those multiple epochs, we will have a final trained model. This model can be used to test the performance by giving it some unseen data, right? So when we give the unseen data, like I said, that the model is going to make a decision based on the output probability. So for a binary classification problem, it's quite simple. We can define a confusion matrix similar to what I show. So you can have a true prediction of 0, and the model may predict correctly 0, which will be a true negative, or it may predict 1, which will be a false positive. Similarly, we can have a true prediction of 1, and the model may predict 0, which is a false negative, or it could be 1, which is a true positive. Based on that, we can define some metrics, so like the sensitivity, which is the true positive rate, or the ability of the model to basically predict seizures in this case. The specificity, we can also define the false positive rate, which will be the ability of the model to predict correctly predict no seizures, and that will be significant. And then we can calculate the overall accuracy, which is the true prediction, whether false or true, over the total number of predictions. So now with that background, I would like to take you on my along on my model journey. So when I did this deep learning model design over the past 2 years, it has been a journey and we have evolved our architectures. So I would like to take you along on this journey. So imagine you are given raw EEG data at the beginning, right? So the first architecture that we designed was based on the residual neural network. And this was a ResNet model that had been trained on ECG data to predict cardiac abnormalities or heart abnormalities. Right? So, and I use that because more people have cardiac diseases, unfortunately. So there are larger data sets available, which means that the model was trained on more data. And then I applied transfer learning techniques to train the model. At the end, we had our final validated model. The architecture of the residual neural network that I modified and used transfer learning on is given below. So we have one convolutional block followed by 4 residual blocks. Each residual block had 2 convolutional blocks. What is the convolutional block? It contains the convolution operation followed by batch normalization, followed by ReLU activation and a dropout layer. So these are some of the details that we can discuss later. So basically, each of these blocks is showing some of the hidden layers that are implemented in the deep learning overview that I gave. Anyway, so to continue, this was my first model. I named it Spirtle, and it gave good enough results such that we were able to file an invention disclosure with FIU, and it has been licensed, and it is being used right now, and I will give more details on that later if there's time. It was very successful. It was also published as a conference paper. However, the performance was good for subject-specific prediction, but it did not generalize well to subject-independent prediction. So in the next stage, we decided to develop our own model. And because the transformer architecture has revolutionized the generative AI and the field of deep learning, and it has also in research been shown to work very well with time series data such as EEG, we developed a new architecture or lightweight architecture based on the transformer. So however, because it's a new architecture, we have to do complete training rather than transfer learning. So this is the architecture. We have an embedding stage. We have to add a classifier token because we are using it for classification, whereas transformers were used for generative tasks or are used for generative tasks in general. After that, we do our positional encoding, followed by 2 transformer blocks. Each transformer block consists of a transformer layer, followed by normalization, and then a fully connected layer followed by another normalization. For classification, we use the fully connected layers with ReLU activation. This model improved the performance compared to Spirtle. However, it still did not push the boundary beyond 70%, whereas we need above 80% or above for the prediction models to be useful. So in the third stage, we continued with this architecture, but instead of designing a new one, we decided to train or use pre-trained architecture. So we use 2 pre-trained vision transformers, SWIN and SegFormer, developed by Microsoft and NVIDIA respectively, and they give very high performance on image processing tasks. However, we had to customize our EEG data such that it can be processed by the vision transformer. So that was the first contribution. The second contribution was that we adopted it for the classification task, where we removed these were trained for, I believe, image segmentation. So we replaced that with the classifier head. And so this is one example architecture. So the common theme is a lot of these pre-trained architectures, they actually contain 4 stages. So they have an input stage and a classifier stage, and 4 transformer stages in the middle. And this is quite relevant because it allows you it gives you a lot of retraining combinations, right? However, initially what we did was we only trained the input layer and the classifier head and kept all of the weights or the parameters of the middle layers frozen. And then we retrained only the first and last layers and got a better performance. So I'm going to detail the performance in a later slide where I have all the results. I'm just going over my model development journey at this point. So then In the fourth stage, we continued with the same architectures. However, we came up with a smarter retraining strategy, which was optimized. Because if you see, if you include all of these stages, there are multiple combination possibles. In fact, the number of combinations are 2 to the power n for n stages. So in case of 4 stages, there is there are 64 combinations. And then these are for each architecture, for each data set type. And when you train the model, you try different hyperparameter combinations. So you can have multiple tuning parameter sets. So all of this leads to exponential complexity. So we made two contributions. The first one was proposing a heuristic algorithm that reduces the complexity or in terms of the number of experiments needed. And then so that was our first major contribution. The second one was to actually use that strategy to generate the best results for each of the benchmarks. So that was the fourth model that we designed. I named them swim optimal or seg optimal or swim opt for short. These are the new architectures. The last, so this did improve the performance. However, we were still hitting a ceiling. So in the last stage or my most recent work, what we have attempted is to add custom layers to the pre-trained architecture. So we take the pre-trained architecture and add a custom convolutional network at the beginning. And for retraining, we switch back to a partial retraining. And in the next stages of the contributions, we are going to combine our optimized training strategy with these custom layers to even push the performance further. So these were all of the 5 architectures that I have developed over the years. So just to give a snapshot of the AUC curves on the left, you would see the ROC curves, and going back to the intro slide that I gave. So we can calculate the TPR and the FPR for a binary classification problem, right? So if you plot the FPR on the x-axis and on the TPR on the y-axis for different probability thresholds, that would actually give rise to these receiver operating characteristic curves, or the ROC curves. So what you see on the left are the ROC curves for the first models, including the ResNet, the VIT, and the ESP former. And on the right, you see the curves for our custom designed models. So it is not very visible, but in a lot of cases you see. So what we actually want is the FPR to be as low as possible when the TPR is its highest, and that is more pronounced in our like custom design architectures compared to the pre-trained. And this would be clear if I give you the snapshot of the results here. So at first, like I said, if you look at the model one, for each of the 12 benchmarks of the data set that I created, if you average out the AUC score, so these ROC curves, what we can do is calculate the area underneath it, and that gives a good idea of how the model will perform in terms of the accuracy and the sensitivity and other performance metrics. So once we do that, we find out that the ResNet average accuracy was around 69%, and the ESP former, the average accuracy of that was around exactly the same, in fact. So later works, we have actually run more experiments to take an average of 10. So what I observed is that the ESP format is in fact slightly better than the ResNet. So that justified the use of the transformer architecture. If you look at the third models, which include both SWIN ESP and SEG ESP, the performance increases. In fact, for SWIN, there is no increase, but for the SEG-former-based architecture, we see a slight increase of about 0.7%. Again, not significant enough. So that is why we moved to our optimization strategies. And here we saw a more significant improvement of 2% or more in the AUC score and 3% compared to the original architectures. However, the best improvement that we saw in the AUC score was with the when we added our convolutional architectures. The best one was the SEG-former with 1D convolution. So convolution could be 1D or 2D. So 2D is usually used for images, and our results match the literature where the 1D convolution addition works best for the epileptic seizure prediction task. However, the AUC score alone is not enough, so that is why I go further ahead, and I would like to. So what I did was I picked the best model from model 1. So model 1 and 2 only have one architecture, but 3, 4, and 5 had multiple architectures. So I picked the best of each, and I compared the results. So in terms of the prediction sensitivity, actually our fourth model, which is based on the optimization strategy, gives the best results. So it has the highest sensitivity of 76%. Unfortunately, the specificity is too low, which means that there would be a tendency to generate false alarms. In contrast, the fifth model gives the best overall accuracy and a reasonable sensitivity of around 71% with a good specificity. The other actually point is that with the higher AUC scores of the fifth model, we can in fact use different thresholds. So all of these results are assuming a probability threshold of 0.5. If we optimize the thresholds, we may actually able to push the performance of the sensitivity further. So these are all good results going in a good trajectory. However, as you can see, the best sensitivity is still around 75%, whereas we need to go beyond 80%. In fact, for clinical use, maybe even beyond 90%. So for subject independent seizure prediction. So that means that there is a lot of model development tasks needed to be done, and that will be the subject of my first proposed research. But before we go there, I would like to conclude this section by just showing, as I mentioned, that in the fourth stage, we came up with a heuristic algorithm to improve the to come up with an optimization strategy, right? So originally we had 2 to the power n combinations, and if we do an exhaustive search of all combinations, if you see the plot with the black circles, these are the number of experiments. So for four stages, that would be more than, I believe, 1,000 or around 4,000 experiments that are needed to be done. And these are deep learning experiments with transformer architectures that take around 6 days to train. So each transformer takes about 6 to 7 hours on 12 benchmarks, may go up to 4 to 5 days of training. So reducing the number of experiments is very useful. So our proposed heuristic algorithms brings that down to about 900 or 800 experiments, a fourfold reduction. So if you have a machine, if you design an experiment that was going to take 60 days, with our approach, that would take 15 days, which is more reasonable for large-scale research projects. On the right, I show a figure where that is the worst case, where if you only have one architecture with one transformer stage, with one set of hyperparameters to tune, then in that case, our proposed strategy would not make sense. You can do the exhaustive search, but that is just one architecture and it's not really tuning. So I just wanted to show the performance gap, and also to show that, and one point I want to mention, so you would see that there are multiple curves, right, in the red and green. So there are multiple curves because our proposed heuristic algorithm took the exhaustive search and broke it down into 3 parts. The most heavy part, or the heaviest part, is the second stage. And in the second stage, you can have different number of experiments. So I tried different combinations, including log and n log and up to n cubed. And as the plot on the left shows, that no matter the complexity of the second stage, if you have a large number of transformer stages, like these large language models that have 16 or more stages, then at the end, all of these will converge to a specific point, and there will be a significant performance gap compared to the exhaustive search. So this concludes the machine learning part of my results. Now I will move to the second thrust, which is about implementing the models at the edge for both inference and for real-time learning. So traditionally, the approach is to actually train the models offline and then deploy them on the edge devices such as wearable sensors, right? And we tried that approach as well. So on the left, if you see the figure, we actually acquired a wearable EEG headband, and then we set it up such that it was transmitting live data to both a Windows PC and a phone. And then my ResNet architecture, the original architecture, we actually deployed it on the phone and Windows, and evaluated the communication performance or with the machine learning tasks included. So some of these results are shown on the figure on the left for different duration of segments. So the smaller duration is preferred because we want real-time results. But as the plot shows, if you use a 5-second duration, then you are going to get a lower performance. I also tried to come up with a simulation test bed that would demonstrate how well the models that we have designed on clinical grade data sets would translate to wearable data. And because the data from wearable sensors is going to be noisy, it will have less channels, maybe 4 or 6 channels, right? Because we want something that people would be able to wear in their normal life, like a bandana or a cap. So the experiments I did were on an EEG or a wearable EEG that is shaped like a bandana, because we don't want people to be conscious. There are enough social and emotional implications as is of epilepsy. Then the data will be streaming, it will be coming in real time, and it's imbalanced. So seizures, while someone, for example, who has 1 seizure per day, it may be very significant for the parents and themselves and their caregivers. But in terms of mathematical representation, that's a rare event, right? So 1 seizure, 30 seconds out of 24 hours, it's still a rare event. So you get this streaming data where most of the time, nothing is happening, and then suddenly an event will happen. So it is kind of imbalanced. And then with wireless capabilities, like the wearable headband that we use had Bluetooth capabilities, you have additional fading and multipath effects. So I developed a degradation model. And then here are some of the interesting results. So for example, on the left, you see the figure that on the top left, you see the performance, the baseline performance. On the bottom, you see the performance after these degradations. So some subjects, some cases, you see, for example, in the red, there is not a lot of difference using variable EEG based on the simulation model. But in other cases, the performance becomes like chance, basically just simply tossing a coin. So this showed that we cannot just take the models and then put them on the edge device as is. For long term, there needs to be some form of retraining mechanism. And here my final like part of my research comes into play. And some of this work I did during my PhD as well, where we try to train the model in real time. And one of the most famous techniques to do that is federated learning at the wireless edge, or distributed machine learning at the wireless edge. Before I proceed to that, I just want to show on the plot on the right, I extended this framework on a simulation bed to testing or doing inference for EEG seizure prediction and for ECG-based arrhythmia detection in real time, and able to offer significant energy savings and do the task within a time constraint. However, we still need to develop the training platform. So before I jump into that, let me just give an overview of wireless edge machine learning before I jump into that. So consider in a small geographical area, you have EEG users that can communicate with the mobile base stations or any edge server, such as a wireless router or similar. And you have multiple such users in an area, right? So up to K users. Each user is going to collect their own data, right? So traditionally, what would happen in the centralized approach, all of the users were going to send their data to the edge server. The edge server would collect it, send it to a remote cloud. The cloud would stack the data together and then train the machine learning model, right? So do all of the passes and then come up with the final trained model. Now for inference, what would happen is each user would collect their short-term data, send it to the cloud, wait for the results would come back. And this was implemented quite efficiently. However, the number of devices at the wireless edge and the number of IoT devices has exploded, and it puts an unnecessary strain on the backhaul links, leading to severe delays. Furthermore, the biggest problem is that if I quickly go back, you see here, the users are sharing their data with the server. And this violates privacy constraints, especially in the medical domain where we have strict HIPAA laws. That could be problematic. So there is no inherent privacy preserving. And that is why the federated learning was proposed. So what happens in federated learning is that each user has their own data, but rather than sending it, they each train their own machine learning model, as shown by the different colored rectangles. So now each of the user has their own model. In the next stage, they share the model rather than the data with the edge server. The edge server comes up with the global model after aggregation. And once this is complete, it shares the global model or the best model with all of these edge devices. And then the model is stored locally, and the devices are going to do inference locally. The thing that makes this possible is the increased computational power at the edge devices themselves that are equipped with high performance CPUs and GPUs. So So as you can see, there are two important parameters here. So one is the data set size that is going to influence how efficiently a user can do their own prediction, or how efficiently they can train the model. And the second is the number of local updates or the number of epochs. So both are key parameters. The traditional research, what it did was it tried to optimize the number of local epochs and the wireless communication parameters or the underlying parameters without really paying attention to the data set size. And here's where my contribution came, and I contributed during my PhD work. So I'm going to skip over some of the mathematical details to preserve time. The main point is that my proposed approach, it actually was based on solving a polynomial, whereas traditionally these type of methods are solved using optimization techniques such as the interior point methods. And it was much lower in complexity and also provided better solutions. So if you look at this chart here, I tested my proposed techniques on two different data sets, and there is a clear difference in the performance when we consider the data set size, as shown by the blue curves with the circles, as opposed to the red and pink dashed lines that show the performance when the data set size is not considered. So my methods were able to improve the performance significantly. Furthermore, the optimization solution that I discovered, the complexity as shown by the blue circles was comparable to the complexity of solving only with the local updates. So with the same complexity, we were able to offer a 1 to 2% improvement in machine learning. And as we saw from previous results as well, 2 to 3 performance is significant, especially when we are considering critical tasks. So this was my contribution towards real-time training. So now the vision for the future and my plan for the next 3 years at least is to come up with a pipeline where we have robust data sets for subject-independent seizure prediction and develop advanced machine learning or deep learning-based architectures that push the performance beyond 90 or 95%, right? And then we want to deploy these models at the edge for inference, of course, but at the same time, we want to have this retraining pipeline where the deployed models, as it sees new data, is able to retrain in real time with distributed techniques, such as federated learning or others, and I will talk about this in a few moments, right? And then the cycle continues, right? Because then we are acquiring new data, and then the model is retraining, and then it's being redeployed for edge and so on. So this is the pipeline that I aim to develop. The first part would again, as I mentioned at the end of the when I was discussing the first source, is to develop new architectures that push the performance boundary. And after having tried vision transformers and LLMs, which I did not cover in this talk, but we also tried LLMs with text-based representation of EG data, VITs, where we use the image representation, and then our custom design architectures, which use raw EG data, and then there is another path where we can use handcrafted features. So my vision or my proposal is that we should use all four architectures, because as we saw that different architectures provide different levels of performance for varying benchmarks or varying data sets. And in the real world, that will translate to people with different types of epilepsy and different types of seizures. So after training these four paths, we will have four different models, and we need to assign a weight to each of the model. So in the last stage, I propose training either a simple regression model or an ensemble regression model to come up with the best contributions from each model for different subjects, for different seizure types, that would result in a predictive model that may push the performance boundary beyond 90 to 85 to 90% that we see. And this has a lot of potentials for collaborations and a lot of potential for undergraduate research. And in this talk, towards the end of this talk, I would like to emphasize undergraduate research projects. And I think this would be of interest to some of our newer members of the lab, undergraduate members as well. So for example, not a lot of work has been done, at least with transformer and handcrafted feature extraction. And this was, I think, clear from my talk. So this is an area where there could be significant amount of contribution, because the underlying techniques that are used, such as statistical methods or frequency domain-based analysis, are all techniques that are taught in courses such as signals and systems or probability and statistics. So this will be a good research contribution where you evaluate the features that are used in the literature and then come up with techniques that are going to extract features that are most suitable for transformer-based architectures and custom architectures that combine the residual and attention mechanism of the transformers. The second area where the contribution can be is more of the implementation side, where these models or these architectures that are designed need to be now trained and deployed in the most efficient way, such as using the retraining strategy that I have developed earlier. And this would give valuable experience with tools such as Hugging Face and Weights and Biases. These are tools that are used in the industry, so it will have a research contribution, may lead to peer-reviewed publications, but also will be a very valuable skill set for the industry for undergraduate students. So this was with respect to the first thrust. In terms of the second thrust, if you recall what I proposed with the federated learning on my previous work, it still requires the edge or users at the edge to share their models with the edge server, and it has been shown in the literature that this can make the system susceptible to reconstruction attack, where the models can be used to reconstruct the data. So to avoid and then again, training the whole model, such as the transformer-based architecture, may be not feasible for edge devices such as smartphones or wearable EEG sensors, for example, right? So split federated learning has been proposed as an alternative that is more secure and less computationally intensive, right? So in the proposed work, what I plan to fill the research gaps. So the first gap is that nobody has really studied the convergence of transformers. So convergence is an important property that shows that as you train the model, your training loss and validation loss will converge to a small value, ideally near zero. And this has not been shown previously for transformer-based architectures for split federated learning. And this is where I plan to contribute. The second area where we can contribute will be optimal allocation protocol. So again, we have multiple such devices, right? So you have either EEG devices or EEG devices connected to edge devices like microcontrollers or smartwatches, right? So, and they're trying to train this model. Different types of devices will have different computation capabilities, and the communication links would also be of varying strengths, right? So we need to come up with optimal protocols in terms of the number of local updates performed by each device and the dataset size used. At the end of all of that, we will need to implement it on the devices using this strategy. So we train all of the models, right? Come up with a plain architecture. So the top row is the first thrust. And then once we have a validated model, we need to deploy it to the edge server. And this is where a lot of contribution can be done by undergraduate students, especially those who are in the embedded systems concentration and have experience with microcontrollers or FPGA-based devices, right? And then the SFL protocols that we develop will also need to be implemented on these devices, right? So not only deploy them for inference, then elevate that by collecting real-time data and then labeling it. And this is something that I can explain if there are questions, because this is always a question: how will the data be labeled? So I do have a strategy in mind for that. And if there's time, I can discuss that. But once that is done, we retrain the trainable layers. We will have an improved model, hopefully. And then we deploy this final model at each of these edge servers. So this wraps up the whole proposed research strategy. Of course, there are additional projects that I have in mind. For example, extending this work to other domains. One of those is cardiac monitoring. Like I mentioned, a lot of people suffer from ECG, for heart diseases, and a lot of ECG-based work is now incorporated into Apple smartwatches and phones. So there's a lot of research potential there. I also want to come up make sure that work towards applying it to other areas such as UAV-based, disaster recovery systems that can also be used in either healthcare or military type of settings. So these are all potential extensions or applications. Before I conclude, I would like to briefly shed light on some of my teaching experience and proposed teaching. So in the past, I have taught undergraduate courses, including Communication Engineering 1, Digital Logic Design, Electric Circuits for non-EE, which is one of the most significant, I believe, contribution, because it allowed me to deliver concepts or circuits concept to students who are from other fields. And this is something that I think at a liberal arts college would be something that is pertinent. Further, I have, since 2019, I have taken on extensive mentorship roles. So two of my graduate students, actually three of my graduate mentees, published multiple peer-reviewed articles, and I will speak to that. The thing, one of my most recent teaching experiences or rewarding experiences were quarter-day workshops that I gave for hands-on ML AI training. And this was a workshop for the NSF Access Step program. It is a female-led program. It is especially directed towards students from the underrepresented minorities, to encourage them to have careers in the cyber infrastructure, including cybersecurity and machine learning. So I gave the machine learning workshop, and this is some of the feedback that I received from both the organizers, from some of the students, and also my supervisor, whose support I would like to acknowledge. Like I mentioned, so two of my graduate mentees published 3 peer-reviewed articles between them. And for example, all of this transformer-based work that I have done is a significant contribution of Paras Parani, the edge-based work of Abhishek. I also have undergraduate mentorship experience where Hermes was a contributor in our technology translation related work. And I didn't speak to that a lot, but this was part of the I-Core program, or NSF's I-Core program, which encourages researchers to do customer discovery and is aimed at helping researchers and also undergraduate students commercialize their research and form startups. So it wants to encourage the technology startup culture in the United States of America. So Hermes helped conduct some of these 130 plus interviews that we did, and was part of the I-Core program. Another mentee, Osizumon, was also a contributor in the lab, where she helped research some of the seizure detection algorithms in the literature. We did not publish that as a peer review. However, it formed the basis of one of the research grants that we actually wrote and won later on. She graduated and moved on to other adventures. I also have other experience mentoring PhD students as well, where we published a peer. During my PhD, I helped a PhD student in transportation engineering publish a peer-reviewed article, conduct experiments that formed the basis of her PhD. As part of my teaching philosophy, I aim to promote collaborative and active learning. So I will just give one example, or actually I will give two examples. So first, the quarter-day workshop training was actually very helpful for me because it allowed me to use Jupyter notebooks as a teaching tool. It's very interactive. So we did the derivations in using the markdown cells, and then we're able to show the results with the implementation using the code cells. So I would include it in other lectures as well. So I think a lot of signal processing work now is being done using Python-based libraries rather than MATLAB. It has multiple advantages. One, again, the interactive nature, and secondly, it is open source, so it will be available for all students. Another example is the jigsaw exercise, which I like to do 1 to 2 times per semester. So just to explain, we divide the classroom into multiple groups, right? Each group is given a problem to solve, and that forms the expert groups. So after each group has solved their problem, you have a set of experts for each particular problem. Then you pick one expert and assign them to a new group from each of those to form the teaching groups. So in the teaching group, you have an expert that has solved, you have multiple experts, each of them that have solved different problems. And hence, all of those experts are then able to explain their problem and the solution approach to their peers. So this is an active method, but it also promotes peer-to-peer and collaborative learning. In terms of the courses, there are several courses that I am so because of the interdisciplinary nature of my work, I can teach a wide spectrum of courses. Some of those that I have listed from both ECE and actually, if needed, even from the CS department. Uh, so just to conclude, my research is an interdisciplinary work that focused on deep learning and machine learning model design for seizure prediction. And the second aspect of that then focus on how to deploy them at the edge for real-time inference and training. As part of my research experiences over the past few years, I have gained a lot of experience teaching some of these concepts and mentoring students, including undergraduate students. And I would be very excited to bring this research experience to new positions and combine them with my teaching expertise and duties. Uh, at the end, I would like to acknowledge all of the people who have helped me along in my journey. First of all, of course, Florida International University and the College of Engineering and Computing for providing the right environment. The funding agencies, including the National Science Foundation, that has funded the bulk of my research, including from the technology translation perspective, as well as NIH, which partially also funded some of the work. Last but not least, I would like to express my gratitude towards the School of Computing and Information Sciences, especially Saeed Lab, under the directorship of Dr. Faz Saeed, who has been my supervisor during postdoc and has helped support all of these research and teaching endeavors. So I would like to express my thanks. I also would like to express my gratitude towards some of the lab members, especially some of those undergraduate students who actively helped, Hermes, as you can see in the red, who actively helped and do some of these experiments, and the graduate students such as Paras Parani, who helped implement a lot of my deep learning architecture designs, Fahad, who has been invaluable for his feedback and his expertise on deep learning as well. And then I would like to thank you all for attending my talk. And I think I may have exceeded the time by about 4 to 5 minutes and not left enough time for questions. But again, I would like to thank you for listening attentively, and I would be happy to answer any questions. Thank you so much.